Alright, so we'll get started with a discussion on chemical admixtures. If you take a look at your book, that is Mehta and Montero, this is in the sections 8.1 to 8.4 of your textbook. So primarily we are looking at additives that are included in concrete from various perspectives, primarily to make an influence on the early properties of concrete, either in terms of workability or sometimes imparting properties that are required for long-term performance. So let's take a look at major aspects of admixtures in this chapter. Before that, officially, what is a chemical admixture? It's an additive to the concrete mixture that enhances the properties of concrete in the fresh or hardened state. So again, very generic definition. Obviously, there are functionalities that each admixture gives, which are not the same across admixtures. Nevertheless, for the purposes of definition, we don't include paints and coatings that are applied on the concrete surface or on the steel surface separately as an admixture. As the name implies, admixture means you're adding this to the concrete mixture. It's not an English word, it's a concrete technology word. You'll not find this in the dictionary. Okay. So if you look at the official definition by American Concrete Institute Committee 116R, it says admixture is a material other than water, aggregates, hydraulic cement and fiber reinforcement used as an ingredient of concrete or mortar and added to the batch immediately before or during its mixing. So something that we put into the concrete. Now, if you look at the class of chemicals which are waterproofing agents, there are different types of waterproofing agents. There are some chemical admixtures that you add along with the concrete itself. On the other hand, there are also other waterproofing agents that are actually used as coatings on the concrete surface. You are probably aware of some of these which are used in typical households and so on. But it becomes an admixture only when it is put into the concrete mix, okay, either during the mixing or just before the mixing of the concrete. Now, there has been historical evidence of use of chemicals of different forms for centuries. Okay, for instance, if you look at the Roman times, they had added blood or eggs to lime mortar for improved workability. A lot of Chinese heritage structures, they've actually found traces of having used blood as an ingredient. Blood is quite interesting from the perspective of its ability to actually make the mixture more cohesive, right? And of course, doesn't mean that we cut open our bodies to put blood into concrete. Nowadays, we have chemicals available, but in the past, I presume it was animal blood and not the person's blood who was actually doing the mixing himself. So yeah, blood and eggs. Eggs are quite common in India also, in several locations of India, especially in the decorative plasters that were made with lime. Eggs were a common feature. If you go to Chettinad type of construction in southern Tamil Nadu, that is also incorporating the egg yolk, egg white as an ingredient in the lime mortar. And that egg white basically gives the nice glassy finish to the exterior surface of lime mortars. In 1230, you have D'Oncourt, who suggested impregnation of lime concrete with linseed oil to make it impervious. It's probably one of the first documented uses of a waterproofing agent, right? Linseed oil is of course, most oils are water repelling. They don't mix with water. So if you impregnate concrete with this kind of wax or an oil, it's not going to allow water to come in. So that's probably one of the first uses of waterproofing agent. Calcium chloride, which is well known as a very good accelerator for concrete, setting accelerator for concrete. The first use was described in 1873 in Germany. And before World War II, air-entraining agents were used in the US, and this was found accidentally based upon certain types of chemicals that were being used. And again, what these chemicals were, essentially, these chemicals led to the development of the later age water reducers. Polynaphthalene sulfonates, which are well known as water reducing agents, were actually used to disperse carbon black in concrete just before World War II. And that it was determined that these were actually giving rise to the air entrainment. Now, air entrainment is typically required in concrete when we want resistance to freezing and thawing. So again, this gave birth to a different class of chemicals which we wanted to use for specific purposes to make concrete durable in certain environments. Now, a lot of high-rise developments in Chicago led to the development of the first water reducing chemicals. So already polynaphthalene sulfonates had been used previously, and they found that using these polynaphthalene sulfonates, they could cut back on the water also to produce concrete that was workable enough, and in doing so they were able to enhance the strength of the concrete. Now obviously the primary use of high strength concrete would have come about for the high rise buildings. I don't know how many of you are familiar with the skyline of Chicago. Many of you may have seen pictures of it. It's got the most amazing set of high rise buildings that you can find in a city, even better than New York, because each building is an architectural marvel. But that's where a lot of the initial technologies for high rise buildings were investigated, and this first usage of water reducers officially documented was with the high rise buildings in Chicago. And soon after that, in 1962, the standard for chemical admixtures, ASTM C494, which is now the benchmark worldwide with respect to standards on different types of chemical additives, that was first released. 1979, first use of corrosion inhibitor in concrete, and today of course corrosion inhibitors are still trying to find inroads into the market. They are not as prevalent as they need to be, but yes, people have started realizing that you can use corrosion inhibitors in concrete as a protection mechanism against corrosion instead of trying to protect the reinforcing steel, which is a much more expensive proposition. And in 1996, the shrinkage reducing admixture started getting used. Now shrinkage is a major problem with concrete, as we discussed earlier. You can add additives to the concrete mixture to take care of shrinkage also, and first use was documented in 96. Late 1980s, there was advent of flowable concrete. In Japan, people started using self-compacting concrete. Of course, people had been experimenting with trying to make concrete very workable, and in the late 80s, the first set of official applications of self-compacting concrete came into being. One of those were quite popular in the bridge which we call as Akashi Kaikyo Bridge in Japan. In any literature in self-compacting concrete, that's one example that you'll get to read. So from then on, SCC became quite popular, and from then we come to a new era of high range water reducers that are specifically formulated for the purpose of concrete usage. In the past, whatever people were using were chemicals from other industries that were applied. Just by trial and error, they tried to find out whether these could be useful for concrete. But later, with the advent of new generation HRWRs, that's when people started actually developing these chemicals for concrete usage. Most of the historical development is captured in this paper by Malins, 1984 paper. It's in Concrete International, which is one of the interesting journals from American Concrete Institute. Now this journal of course is not very academic in nature. It emphasizes a lot on concrete practice and also deals a lot with the current developments in the concrete industry presented to a more wider audience than actual researchers. So it's quite an interesting paper for you to read. Of course, for those of you who are taking the course now, I'll have it uploaded on Moodle, but people who are taking this course online, this paper is available for download from Concrete International. If you become ACI student members, you can actually become student members of American Concrete Institute for free. Okay, you just need to produce your documentation showing that you are a student, and you will be able to become members for free. That will give you access to the Concrete International publications or journals like Concrete International and ACI Materials Journal, which can help you download these papers for free. Okay, right. Now, for the purposes of modern day construction, we divide chemical admixtures into various categories. The most common categories are the water reducers. Then we have set controlling chemicals, either set acceleration or set retardation. Okay, and then we have air-entraining chemicals, which are introducing air wantedly into the concrete for the purposes of providing durability in freezing conditions. And then you have specialty admixtures, which could be of different types. Sometimes you want to make your concrete thixotropic or stabilize high flowing concrete and prevent segregation, so you use viscosity modifiers. You want to protect the steel from corrosion, so you inhibit the corrosion from happening inside the concrete, which can be a mechanism both affecting the steel or the concrete. So in this case, we call it corrosion inhibition, or corrosion inhibitors are the admixtures that are used, and shrinkage reducing admixtures for the obvious purpose of reducing the extent of shrinkage that happens in concrete. There are also polymeric materials like latexes, which are used in concrete primarily for providing some flexibility and better bonding ability to repair materials that are applied to concrete. Now, every time you do patchwork with mortars, right, when concrete is broken off or spoiled off from a section of the building, we use these special mortars to patch up these locations and to produce patches that bond well with the substrate and also have very little shrinkage. One of the common ingredients that we use in such mortars is latex. Latex is basically rubber, right, polymer, which is basically derived from rubber. And there are other specialty chemicals which we can use for other purposes, which we will talk about later in the course of this chapter. Now, specialty coatings also include curing compounds. Now, curing compounds are technically not chemical admixtures, but we will still have a discussion of those because they are getting increasingly important in this day when we have little access to good quality water for construction, right. We of course need water for making concrete, there is no doubt about it, but the water for curing can be avoided to some extent if we apply these curing compounds in a proper manner, right. Now, if you look at all the classes of chemical admixtures, there are some common characteristics that we have. One very important characteristic is all of these are water soluble. All the admixtures that are added in the concrete have to be water soluble, because if they are not, then they will not get mixed up in the overall concrete system, right. They will remain as such. If they do not mix in the water, if they do not dissolve in the water, they will not get distributed evenly in the structure of the concrete. Mostly these chemicals are organic. Of course, that does not mean inorganic chemicals are not used. Like I already told you about calcium chloride, which is a very effective accelerator. There are inorganic chemicals also, but for the most part, most chemical admixtures are organic. And as a result of them being organic, it is obviously helpful for us to understand the polymer structure, because organic chemicals are basically polymeric in nature, and water soluble polymers are what we are interested in. So, just to help you recollect what you learnt in your most favorite subject in school, organic chemistry, I will talk a little bit about polymers. Okay. So, of course, you know that polymers are composed of many units of individual components, which we call as monomers, or sometimes we just call it mer, right. Single block is a mer. Okay. And there are different ways of polymerizing. You have obviously the addition polymerization, in which the same unit keeps joining together under some conditions of temperature and pressure. Alternatively, you may have two different mer units which come and join together in a reaction which we call as condensation. So, you have either addition polymers or condensation polymers. Now, of course, when you go through admixture chemistry in more detail, you will see that most polymers are produced by the condensation mechanism. And usually to have this condensation happen, you have additional chemicals that you need to actually pump into the system for enabling this condensation to happen. Okay. So, one important aspect as far as the effectiveness of the polymer is concerned is the length of the polymer. Now, length obviously means how many units are joined together to make the chain. So, if you think of a polymer as a chain, how many links are there in this chain, that defines the overall length of the polymer. The length obviously also affects the molecular weight of the polymer. The greater the length, the greater the molecular weight. Okay. So, when you start looking at the mechanism by which these polymers interact inside the concrete system, then you will start appreciating why this particular aspect of length of the polymer is important. Now, the structure of the polymer could be different. Some polymers are long chain polymers like this, some other polymers may be branched, okay, and you may have side chains of the main polymer that are quite large and bulky. Again, when we look at the mechanism of action of some of the water reducing chemicals, you will understand how these polymer structures tend to affect the overall performance of your polymer. Okay. Some polymers may carry a charge. There may be some counter ions present, right. Either a positively charged or negatively charged system may be present in the polymers. Again, this influences the way that these charged particles or charged polymeric chains interact with the cement to lead to certain properties in the cementitious system. As I said, you have copolymers in which you have more than one type of unit to make the polymer. Okay. So, all of these aspects need to be understood in a much more detailed fashion if you want to go into chemical admixture manufacture, because controlling the proportions of the individual components, controlling temperature, controlling the pressure, All of these are critical in trying to get an understanding of what type of ultimate chemical you end up producing. Okay. Luckily for you, you don't have to bother with any of that because you're all civil engineers. So, what we need to bother with is how to use them, but to have some sort of an idea about the structure of the polymers is sometimes important in understanding what makes polymers effective in some situations and ineffective in other situations. We will discuss those when we talk about compatibility of these polymers in cementitious blends. So, let us now look at water reducers in more detail. Okay, that was a 5-minute description of polymers or organic chemistry. That is as much as you will get in this course, but I will show you some polymeric structures and polymer compounds later. So, you will be able to appreciate where these structures are important from the perspective of performance. So, water reducers typically are classified either as plasticizers or normal water reducers, superplasticizers or high range water reducers. Now, what do you think could be the meaning of a water reducer? It reduces water, obviously, right? What is the benefit of reducing water? When you reduce water in concrete, you automatically increase the strength. So, that is the primary impact of water reducers, and as I said, the major development happened in the high rise building industry, where the purpose was to produce higher strengths without using too much water in the system, because produce more water obviously, see, high rise buildings, the other problem is you need to make it workable at higher levels, higher elevations. If you are pumping this concrete to higher elevations, if you keep on adding more water, obviously strength is going to drop. So, you need to increase the workability without adding water. So, that is where they started experimenting with these chemicals that were available. Now, apart from normal and high range, there is also a mid range water reducer. So, all these names are derived from the fact that you can reduce water content to a certain extent with each of these chemicals. For instance, with normal water reducer, you can get 5 to 8% water reduction. With mid range, you can get 8 to 15%. Well, it depends about what people usually use as mid ranges, but most mid ranges will go up to 15% water reduction. High range, typically what is required is 15 to 25, but these days you have up to 40% water can be reduced. Significant amounts of water can be reduced to produce workable concrete. So, what is water reduction? Basically, for a given workability, that means without changing the slump of your concrete, you can reduce some water by the addition of these admixtures, and reduction of that water leads to a higher strength, and because your water cement ratio is low, it also leads to higher durability. So, strength and durability are enhanced, but your workability is constant. Now, what if I do not want to change my water cement ratio? I keep my water cement ratio constant, I simply add this plasticizer, then it increases my workability, it makes my concrete more flowable. Okay. So, I am using these chemicals in concrete by keeping water cement ratio constant. But the most important is the third one. Most important application of superplasticizers in modern day understanding of concrete should be taken as a third one, which says that for a given water to cement ratio and for the same strength and workability level, the quantity of cement can be reduced. Now, how can this happen? We have designed concrete with a particular cement content with a particular water cement ratio. Now, I am telling you that if you use a chemical admixture, you can cut down on the cement. How can that happen? Why am I saying that? So, just for an example, let us say there are two concrete mixtures. Mix 1 has 400 kilograms of cement and 200 kilograms of water. Okay. Mix 2, I have used a water reducer, let us say, which cuts 20% of my water. So, how much do I have? 160, right? I have 160 water content here. Now, I want to maintain the same water to cement ratio, which is 0.5, right? 200 by 400, 0.5. So, technically I should be able to produce this concrete with 320 cement content. So, with water reducer. Does this mean that I can cut down my water to 120 and cut down my cement to 240? Probably not. I mean, you may not get the same effectiveness out of that system, but what you can get out of 400, you can get quite easily out of 320 also. So, what does this mean? You have used some chemical which may add to the cost of your concrete perhaps, but that cost enhancement due to the chemical is easily offset by the cost reduction by using less cement. But more important than cost, carbon footprint. Yeah, today we need to increasingly talk about sustainability, carbon footprint. Less cement you have in your concrete, the lesser is the carbon footprint of the concrete. Less CO2 emission from the concrete, less energy utilization, embodied energy of the concrete is also lower. So, this is a very impactful statement that you can make by convincing people to start using water reducing chemicals. Now, interestingly in our country, there are still a lot of jobs where water reducers are not even permitted. After what, nearly about 70 years of research data have been published in water reducers, there are still organizations that will not permit you to use water reducers. That's really unfortunate, right? Because for M20 concrete, I have seen examples where people have been using 400 kilograms of cement per cubic meter for M20 concrete. Why do they do that? Because they want to get workability. So, they push up their water content also significantly to 200 or 220 kilograms, because without water reducer, you need to have sufficient amount of water to get workability. So, if you do not have that much water, it will not be workable. So, you push up your water, so you also have to push up your cement, because your water cement ratio is what is determining the strength. So, as a result, I have seen several applications for low grade concretes like M20, M25, where people are using as much as 400 kilograms of cement, and that is really a criminal wastage of resources. We have to really put a stop to this. So, whatever you learn from this course, at least learn this one thing: convince your management to use superplasticizers to cut down the cement in the concrete rather than to make concrete workable or anything, which is obviously important. But the most important aspect is cutting down cement usage in concrete. There is no other means of reducing CO2 footprint and energy, embodied energy in concrete, as much as utilization of less cement in concrete, because cement is the single largest contributor to CO2 emissions from concrete. So, cut down cement, you get that, and chemical admixtures can help you do that. Okay. Now, this is a very simple way of looking at it, about looking at water reducers. So, this is the workability in terms of spread measured in a flow table test, and that is the water content of the x axis. So, what does this say? This says that as you increase the water content, the workability increases, flow table spread increases. Okay, let us say this is the curve without superplasticizer. If you add superplasticizer to your concrete, you shift this curve towards the left. In other words, if you choose a given water content, the choice of inclusion of superplasticizer is leading to increased workability. If you choose the same level of workability, you can reduce your water content to get increased strength and durability. Okay, it's a very simple way of actually looking at the entire thing.